Well, thank you, Chen Chen, and thank you everyone for joining us for this online talk. So my talk is going to be on this minimal time min field games, which is essentially the type of min field games that I've been working on recently. And this is quite of new topic I've been working on, which is second order local minimal time min field games. So this is based on a joint work with Roman Ducasse and Filippo Santambergio. And so for this talk, I'll start by an introduction to the topic. So what is the motivation for the kind of games that I'm considering and why I'm considering them and some previous results. And then I'm going to the main part of the talk, which will be essentially the second order local minimal time info games with finite and then infinite time horizon, knowing that essentially the main results for us are those in infinite time horizon, and the finite time horizon just an intermediate step to get to this part. So the main few games I'm considering are based on crowd motion. So crowd motion meaning trying to understand and model the behavior of people, of pedestrians in moving around places like here in the Shibuya crossing in Tokyo. And of course, crowd motion is nothing new. There are many works on that, many books, recent code, mathematically oriented, application oriented, engineering oriented, and so on. So this is a really huge topic. And since we're doing meaningful games, the kind of crowd motion models that are interesting me are the macroscopic models, which means that you want to study the evolution of some density of agents in time. So more precisely, the idea is that in general, macroscopic models for crowd motion will try to model through a PDE like this, the evolution of some density of pedestrians in a certain domain omega here. And so they follow essentially a continuity equation here with some velocity field. And the idea of crowd motion is that people do not choose the velocity field blindly. Their choice of the velocity field depends usually on the density itself in some way. And there may or may not have some viscosity here. Since I'm talking about second order mean field games, I want to have some viscosity later. But in general, for macroscopic models for crowd motion, usually this nu is equal to 0. And this equation can be seen simply as a basic conservation law, in which the amount of people in a certain part, small omega of our big domain omega, changes only according to exchanges through the boundary, either because of diffusion or because of our velocity field G. And so you have many kinds of models for crowd motion, and the difference between them are in the way of modeling how people choose their V, how people choose the velocity field. So there are many ways to model that that are somewhat classical in the literature, saying that people will try to go to their objective, but then if they find an obstacle, they change their V. So there's this kind of adaptation to obstacles and to other people. And the mean field game approach is essentially an approach where we assume some sort of rationality. And so the main idea here is that we're saying that pedestrians will choose their V by solving an optimal control problem, which will take into account the behavior of other people in the sense of taking into account the density rho. And so the goal, the starting point for this work is to propose a mean field game model inspired by crowd motion and take into account some important features of crowd motion. Now, of course, it's important to say that this is not the first or the only work on mean field games for crowd motions or related to crowd motions, or I did some short list here of other works where crowd motion is present either as the main topic or as a potential application of the work. And what you want to do here, which is essentially the main part, is that we want to change a little bit the assumptions that go into the mean field game. So usually mean field games usually have a fixed time horizon where everybody moves, or an infinite time horizon and everybody solves their optimization problem in their time horizon. And what you want to model here is the fact that one agent may take their final time into account when considering their optimization criterion. So we want an optimization criterion with free final time, in which time is actually part of what the pedestrians will optimize. So the idea here is that our pedestrians may stop at different times. They do not have the reason to stop everybody at the same time. And the total travel time may be part of the optimization criterion of the pedestrian. And so usually congestion phenomena are modeled through some sort of penalization, the Lagrange, and so on. And you decided to change a little bit this point of view and put congestion in a velocity constraint. So the idea is that it's somehow a certain way of taking into account some hard congestion, not exactly hard congestion in the usual sense of crowd motion, but it's a hard constraint in the sense that if the density is too high, people cannot move faster, even if they pay an extra price. So they do not have the choice of paying an extra price to move faster, like they do if you just put congestion in the Lagrangian. So the idea here is that we're going to try to model congestion as a constraint in the maximal velocity of agents, which depends on their density. Now, before going to the second order mean-field game, I'd like to present a little bit my previous work with Filippo Sant'Ambrogio and with Samer Dweik on the first order case, because essentially our second order model is based on trying to see what else you can get from this kind of mean-field games for crowd motion. And so the setting is the following. We have a bounded domain omega in RD, which is where players of the game evolve. And we assume that people want to reach a certain target, let's say an exit of the domain, in minimal time. Now, to simplify things in this talk, and also because there are many things you cannot know how to do in the general case, I'm assuming that the exit is the whole boundary of the domain. So the idea is that a player wants to go to the exit in minimal time, and the interaction between players is through congestion, meaning that the maximal speed of a player will depend on the density of other players around them. I'm going to assume that my domain is smooth in the talk, so the boundary of omega is C2. There are many things that can be done with less smooth boundary, but we need C2 for some of the results, so I'll assume this for everything to make it simple. So how do we describe this mathematically? So for me, the evolution of players will be given by the evolution of a probability measure. So at some time-dependent probability measure, OT here, which is a probability measure in the closure of omega. And as usual in the games, I'm going to assume that I know the initial distribution, and I want to determine how this evolves for positive time. And now the dynamics of the player. So the idea is that I want just to have a bound on the velocity. So I say just that the norm of x dot of t is just bounded by some function that depends on the current position and on the measure saying where other agents are. And I can rewrite this as a control system, saying that x dot of t is equal to k times a certain control u of t, which is bounded in norm by 1. And so x here is my state, which is in omega bar. And you're assuming that people want to minimize their exit time. So they want to minimize capital T such that they start at their fixed initial position, and at time capital T, they reach the boundary of the domain while satisfying our control system in between. So the main characteristics of this model with respect to what we usually see in other mean-field games is that the interaction of players here is only through their dynamics, essentially. The control is just minimizing the time. There's a control constraint, so the norm of u is less than or equal to 1. Usually there are control penalizations, but not constraints. And it's an optimization criterion with free final time. So there are other works and mean-field games on that, but this is not, let's say, the usual and classical setting for mean-field games. So let's just get to the mean-field game system formally here. So if we introduce the value function, so phi of tx is the minimal time to reach the boundary for a pedestrian that starts at position tx. So it solves this classically in optimal control, some Hamilton Jacobi Bellman equation. And we have the very natural boundary condition that phi at the boundary is 0 because the minimal time to reach the boundary when we are in the boundary is already 0. And using classical techniques in optimal control, we can get what is the optimal control for this Milfield game, and it is just minus the normalized gradient of phi. And then Ho solves the continuity equation with no boundary condition, because this velocity field always points outwards of the domain, and so we do not need up to give a boundary condition for Ho. And so in the end, we have this Milfield game system here. So the continuity equation for Ho, and a Hamilton Jacobi Bellman equation for phi, coupled here because here this depends on Ho, and here the velocity field depends on phi. So you see that there are some changes with respect to classical setting with penalization, quadratic penalization in U, because for instance, the optimal velocity here is not just the gradient of the value function, but the normalized gradient of the value function, meaning also that we have to take care what happens to the system when this gradient is equal to 0. And we have our initial condition and boundary condition. So what you would really like to do is to treat the local case, meaning that k of Ho tx is just some function kappa of Ho t of x, where Ho t is the density of the measure Ot, assuming that it is absolutely continuous. And typically for k non-increasing, for instance, a very nice k would be positive part of 1 minus Ho. So if the density is greater than 1, people cannot move. If the density is less than 1, people can move, but their velocity depends on the density. But we do not know how to treat this case. So in the first order case, we're only able to treat the no-local case, for instance, by taking k as some function kappa here of some convolution of Ho with some kind of chi, with possibly some spatial weight eta here. And also assuming that we have a uniform lower bound for this kappa here, meaning that people can always move at some baseline velocity aiming here. And then we can prove existence of solutions to this Milfield game system. So the proof that we gave in our first work on that was based on the weak notion of equilibrium, Lagrangian notion. I think at least 3 other people already talked about this notion in the previous talks. It's essentially can be seen as a measure on the set of trajectories, which is concentrated on optimal trajectories. And we prove these using fixed point arguments. For this, we need some regularity of optimal trajectories, semi-concavity of the value function, and the existence of the normalized gradient along optimal trajectories. And these are techniques that are essentially specific to the first order case, because we really need regularity of optimal trajectories. We really use the fact that these optimal trajectories are C11. And so we cannot expect to have to follow the same procedure when our trajectories solve some stochastic differential equation, in which case they'll not be smooth. Other kinds of results that you have here is that if my initial density is in LP, it remains LP with some bounds, and we can also control the norm. And under some assumptions, we may authorize some non-smooth functions eta here. In particular, a very natural one is eta equal to indicator function of omega, because in this case, of the open set omega, because in this case, it means that you'll take people into account as long as they are in the set, but as long as they reach the boundary, we stop taking other people into account. So everything I've said in this short introduction to the first order case is written in these papers with Filippo Santambrogio and Samer Duic. And our motivation was from crowd motion. And what is interesting is that the Milfield game system that we get is actually quite close to another more classical work on crowd motion, which is called the Hughes model, proposed by Hughes in around 2002. And there's one main difference between the Hughes model and our model, which is this time derivative here. So this minus dt of phi here does not appear in Hughes model. And the idea of Hughes model is that to model the behavior of the crowd, of an agent at some time, at some position at some time, they'll try to look for an optimal control that would be the optimal velocity, that will be the optimal velocity if everybody else stayed in the same place where they are right now. And so at this time, they compute their optimal velocity, they move, other people also move, and then they recompute their optimal velocity. So actually, at each time step, people are trying to solve, in a certain way, a static optimal control problem based on based on the current position of other agents, which explain, and the solution of this is given essentially by this equation kappa k gradient of phi minus 1 equal to 0 without the time derivative here. But in the middle field game perspective, we know we have a rational anticipation of how other people will behave. And so we know essentially how Ho will be in the future. And we use this future information in order to get our optimal control at time t. And this is expressed essentially in this minus time derivative of phi, which is essentially bringing information from the future to the past. We can see it like this. Similarly to our case, in Hughes' model, we cannot treat the local case for k. I think there's only some results in the non-local case in the same way as our mean-field game model, but it's interesting to have this comparison to show that if you want to model crowd motion, at least this model seems like an interesting choice. Now, the main topic of this talk will be the second-order case. In the second-order case, what changes is that people will have additive independent Brownian motions in their trajectories. So mathematically, I replace the previous dynamics, which was that just x dot equal to k times the control by k times the control plus some Brownian motion here, the dwt, with some amplitude nu here. So we have the same things that we had before. X is the state, use the control. We have the same control constraint. And I'm assuming that I have a positive nu here, meaning that everybody submitted to at least some Brownian motion. And to do essentially the same thing as before, we're saying that people want to minimize the exit time. Well, the exit time is also a random variable. It is the first time at which my x of t is not in the domain. Just to simplify things, assume that people stop as soon as they reach the boundary. So this process here is only follows this equation as long as they still didn't reach the boundary, and people want to minimize their expected exit time expectation of 2. So why do you want to consider the second order case? So let's say that the main motivation for us is that in the first order case, we wanted to treat the local case. We couldn't because there are many regularity issues that are really hard and possibly not even possible to do in the first order case. So in the second order case, this independent Brownian motion will give diffusion terms in the PDEs. So our solution of the mean field gain system should be more regular. And in this case, it could be we could have enough regularity to treat the local case, which is what I'm going to show here. So I'm going to assume in the sequel of the talk that we are in the local case. And so k of rho tx is just some kappa of rho of tx, where kappa is some function that is, do not need to assume much regularity, continuity should be okay, it should be bounded, and it should have some physical meaning, it should be non-increasing, meaning that as the density of people increase, the maximal speed at which you move decreases, so people tend to avoid the congestion zones. So in the sequel, I'm always assuming that we are in the local case. So my k is given by kappa of rho, where kappa is just a function like this. Now, the problem here is that we want to do that with 3 final times. So we want to minimize the exit time, but not want to impose a constraint saying, well, people must have left by some time capital T. But the problem here is that it has no compact time interval. And if you want to do some fixed point techniques to obtain existence of solutions to the mean field gain system, having a non-compact time interval is not really nice. It makes many estimates much more complicated. This was not a problem in the first order case because you used a very different technique, but also because in the first order case, there exists some time such that all agents live before this time. It essentially depends on the diameter of the domain and the minimal speed that an agent may have. But here, because of diffusion, there's always a positive probability that given some time t, there's always a positive probability that some agent still didn't leave by time t. And so we do not have guarantee that everybody will have left at some time t. So the idea here is to prove existence for finite t and then let t tend to infinity. So for me, t is the time horizon. And I'm going to penalize people who do not live by this time horizon. So I'm going to introduce a function psi, which is 0 if people are on the boundary. It is strictly positive outside of the boundary. And I want, instead of minimizing just the expected exit time, we minimize the expected minimum between the exit time and our fixed time horizon, plus the penalization on the final position here. And then we can introduce, as usual, the value function and get our mean free game system. So we have a Hamilton Jacobi Bellman equation for phi. With respect to the previous one that we had in the first order model, the only difference is that we have now here this Laplacian, so this diffusion, and we have a final condition equal to psi. The optimal control is still given by a normalized gradient of phi, and we have a Fokker-Planck equation for rho with this Laplacian here. And now, since it's a second order equation, we need some boundary condition, which we impose to be 0, because, as I said, we assume that people stop as soon as they reach the boundary. And so this brings us to our mean free game system, which is this Fokker-Planck equation, coupled with this Hamilton Jacobi Bellman equation with 0 boundary condition for both functions, an initial condition for rho, and a final condition psi for the value function. And so in the sequel, what I'm going to show is that we have existence in a finite time horizon, and we can treat the infinite time horizon casing by a limit procedure, taking the time horizon that tends to plus infinity. Okay, so let's go to the finite time horizon, and I want to have existence of solutions. And the difficult part here is this gradient of phi normalized, because for this normalization to make sense, my gradient of phi should not be 0, or at least it should not be 0 almost everywhere, but you do not have this information a priori. So the fact that we have this normalization here brings us some questions on how to define solutions of the system. And so the definition that we get for solutions of the system in the following, the definition that we propose, is that a solution is just a pair here that satisfies both equations in the weak sense, but such that there exists a velocity field such that the Fokker-Planck equation is satisfied with the velocity field v, and this velocity field should be bounded by kappa of rho, and be such that when I take the scalar product with gradient of phi, it gives me minus kappa of rho gradient of phi. So if gradient of phi is different from 0, v is necessarily given by minus kappa of rho gradient of phi divided by the norm of gradient of phi. But if it's 0, this gives me at least some definition of v, so v is well defined, and I can say that I have solutions of this equation here. So for me, a solution of the mean free game system is a pair rho phi and this velocity field v here that is essentially this, but which is also well defined when the gradient of phi is 0. And the main result is that we have existence of solutions. So more precisely, what you need is an L2 assumption on the initial data, an H01 assumption on the final data for the Hamilton Jacobi Bellman equation, and continuity and boundedness of our function kappa. Then there exists a solution, and we have some extra regularity properties of the solution, namely that it is rho is continuous in L2, the time derivative of rho is in L2 age minus 1. Phi is a little bit more regular because we have some extra regularity on the final data here. So it's continuous in H01 and L2 with values in H2, and its time derivative is L2 in time. So how do we prove this kind of result? Now, for existence, the first thing that we do is that we study both equations separately, Fokker-Planck and Hamilton Jacobi Bellman, and then we do a fixed point strategy. To study both equations separately, we need the existence, uniqueness, some energy estimates, and continuity with respect to some parameters that I'm going to make precise a little bit later. And then we conclude by a fixed point argument. So to be more precise, for the Fokker-Planck equation, we studied first the Fokker-Planck equation with some velocity field v here. And it's pretty classical that if v is in L infinity of tx, we have existence and uniqueness of weak solutions in the space L infinity in time, L2 in x, L2 in time is 0 and x, and the solutions are a little bit more regular they're also continuous with values in L2, and their time derivative is in L2 h-1, with an energy estimate here that estimates all the norms that I have on whole in terms of the L2 norm of the initial condition, and a constant that depends on the dimension, on the domain, on the final time, on u, and on an upper bound or on my on the L infinity norm of my velocity field. And we also have positivity, which is pretty classical. If O0 is greater than or equal to 0, then it remains greater than or equal to 0 along the evolution. And the other important property that you need is continuity. And the continuity property that we shall need and that we can show is that if my velocity fields converge in L infinity in space-time weak star topology, then my solutions converge in L2 space-time strong topology. And this follows from the energy estimate that we had before, because thanks to this energy estimate, my sequence of solutions ρn is bounded in L2 h01, and its time derivative is bounded in L2 h-1, which means that using Brownian's lemma, we can get compactness of the sequence in L2 of time space. And when we pass through the limit, we can show that any limit point must solve the Fokker-Planck equation. Since we have uniqueness, this limit point is necessarily whole, and the whole sequence converges in L2 in the strong topology. Now, for the Hamilton Jacobi Bellman equation, we essentially need the same kind of properties. Now, the main difference here is that we have some extra regularity of the final data, and I'm going to show in some time why we need this extra regularity. We still have existence and uniqueness of weak solutions. Now we can prove this in many ways. You can use some classical results of literature. I can just say that this is a linear heat equation with some source term that is this part, and then you do a fixed point strategy. And but because of the extra regularity that we have in the final data, we also have some extra regularity on phi. It is continuous, not with values in L2, but actually in H01, a little bit better. And L2 with values in H2, and its time derivative is L2 in space-time. And we have energy estimates. So one energy estimate with the L2 norm of psi and some weaker norms of the solution, and another with the H01 norm of psi and some stronger norms of the solution, again with constants that depends essentially on the same things as for the Fokker-Planck equation. And for the continuity property, what I have is that if K converges weak star in L infinity, then my solutions converge strongly in L2 H01. And the idea is the same in the sense that we have an energy estimate that gives me boundedness of phi n in L2 H2. The same energy estimate gives me boundedness of dt phi n in L2 in space-time, and then the Brownian lemma gives me compactness. Since these two spaces are a little bit better than the previous case, then I can get the compactness in L2 H01. And now, the extra regularity that I need is precisely in these points, because I want to pass the equation to the limit, and we have this nonlinear term here, which is the norm of gradient of phi. So I want I need some strong convergence of gradient of phi. So I do need the compactness in L2 H01 here, which I cannot get unless if I assume that psi here is in H01. So it's actually this strong convergence that you need because of this nonlinear term here that makes me require some extra assumptions on this term here. And the rest of the proof is the same. So if any limit point solves the equation, and if you have uniqueness of the solution of the equation, then the whole sequence converges to this in the strong sense that we have. And then you can draw a fixed point. And for the fixed point, the strategy is the following. So we start from a velocity field. So for me, V is a velocity field, which its role is essentially the role of minus kappa of rho normalized gradient of phi here. And using this velocity field, I can compute the solution rho of my Fokker-Planck equation. So rho here is the solution of the Fokker-Planck equation with this term here replaced by some velocity field V. And this map, that Triech map, Triech vector field V, maps the density rho. is continuous by what he just proved in these topologies. Then using rho, we can just compute kappa of rho by composing with kappa, and we have continuity of this composition application composition. If we have a strong L2 convergence here, we have weak star L infinity convergence here. We actually have even better convergence, but this is enough for us. And then using this kappa here in this Hamilton Jacobi Bellman equation, we can compute its solution, which should be the solution of these with this boundary condition. And again, I have continuity of this map. And in the end, I want that the velocity field that I compute using kappa and phi from my definition of solution is the same one that the one I started in the beginning. So actually, I define V of V should be the sets of all L infinity velocity fields that are V tilde that are bounded by kappa of rho, and such that V tilde scalar with gradient of phi is equal to minus kappa of rho norm of gradient of phi. Just recall that if gradient phi is non-zero, this is the same thing as saying that V tilde is minus kappa of rho normalized gradient of phi. And so we can show quite easily that we have a solution of this system if and only if we have a velocity field V that belongs to this calligraphic V of V. So if and only if we have a fixed point of this set value function, which is my calligraphic V here. So essentially what I want to do is to apply Kakoton fixed point to this V here. And to do that, I just have to check that our assumptions for Kakoton fixed point theorem are satisfied, meaning that V of V is non-empty, compact, and convex, and V is upper semi-continuous. So non-empty and convex, it's not hard to do. And compact and upper semi-continuity comes essentially from the fact that all the maps that are involved here in the definition of V are continuous, and we can, using that, quite easily prove that V has a closed graph. And this closed graph implies both upper semi-continuity, compactness. So we have a fixed point, and so we have a solution to the mean-field gain system. And this concludes what I want to say about the mean-field gain system with finite time horizon. Okay, so I just showed existence. I didn't say anything about uniqueness. In general, we may not have uniqueness in some situations. What I want to do now is to move on and stop using this fixed finite time horizon property and go to the infinite time horizon. So my mean-field gain system with infinite time horizon is essentially the same, with the difference that equations are now valid not only on the time interval 0t, but for every t greater than or equal to 0. And there is no sense in imposing a final condition on phi, so we do not impose anything. So we have boundary conditions for rho and phi, initial condition for rho, and we do not impose anything on the final condition of phi. As we'll see, we'll prove later that phi necessarily converges to some very specific function that we can identify. So the definition of solution is the same in the sense that we still have the problem with this velocity field. So we also introduce some V that satisfies some properties. And in the case where the gradient of phi is non-zero, then this V should be exactly what he wants. So the normalized gradient of phi. But it also imposes something more. We impose phi to be globally bounded. Now, why do we need the globally boundedness of phi? So first of all, we want to prove existence of solutions. Of course, we can prove that we can have a phi that is globally bounded, but this is also somewhat a natural assumption to put on our solutions, because in many situations, when you're studying optimal control, there are many cases where at least a one-sided boundedness condition on the value function on phi, on the solution to the Hamilton Jacobi equation, is a necessary or sufficient condition to interpret the solution as the value function of some optimal control problem. So when we are solving a Hamilton Jacobi Bellman equation, sometimes it's appear quite naturally, in particular in first order cases, and we can prove existence of solutions with this bounded phi. And actually, boundedness of phi will be a very important property to obtain results on the asymptotic behavior of rho. And it's not unreasonable to think that phi is bounded also, because we are in a bounded domain. And since you are in a bounded domain and people want to reach the boundary in minimal time, and that's what you're trying to minimize, the time to reach the boundary. So phi as the expected minimal time to reach it, the minimal expected time to reach the boundary should be bounded by some geometric considerations. So this is not unreasonable, and this is why we put this in the definition of solution. And the main result is that we have a solution, so we only need an initial distribution that is in L2. Actually, can do it even weaker than L2. I'll say a word on that in the end if I have time. And we need positivity of the initial condition. And then we have a solution in the previous sense with the same extra regularity that we had in the fixed time horizon case. So C2 L2 and time derivative in L2 h minus 1 per whole, and continuous age 0, 1, L2 h2 for phi with time derivative in L2 in time space. But everything in T here is local. So all summabilities that you see here in T are local summabilities. Now, the idea is just they start from a sequence of solutions in finite time horizon, let the time horizon tend to infinity. All that we require, since we're taking sequences of solutions in finite time horizon, is that we want the final condition for phi. We have to fix some. We just fix it as a bounded sequence in L infinity H01 of non-negative functions. So we can fix it as 0. We can fix it as any constant finite condition that you want. We can prove that they converge some equilibrium in all these cases. And so what you want to show is that up to certain subsequences, we have convergence in L2 in time space for whole, and in L2 in time H01 in space for phi. And if this convergence holds, we can pass to the limit in the equations and verify that whole phi is a solution in the infinite time horizon. Because we're considering weak solutions, then we only test against a test function. Test functions have combat support, and so we use only local integrability. And now, so what you want to prove now is just that we have this convergence here. We have compactness of whole in L2 time space, and we have compactness of phi in L2 H01. Now for whole, this is quite easy because we can use the energy estimate that we have in the Fokker-Planck equation. We take some time horizon t, we let Tn be greater than t, so we are far away enough in the sequence. And then we have this constant here that depends on t, whole 0 does not depend on t. So we have boundedness in these intervals for whole and for its time derivative. And so we can apply Aubin-Lyon's lemma to get compactness in L2 for finite time horizons for every time horizon. And so up to starting subsequences and doing a diagonal procedure to get any t here, we get the convergence that we need in L2 log of t, L2 in space. But for the Hamilton-Jacobi Bellman equation, if you try to do the same, we have a problem because of the final condition. Because the final condition, here I put the condition at time 0. Here I should put the condition at time capital T. But my final condition is a time Tn, which is greater than t. So here I should put phi n of t if I want to apply this in t. But I do not know how to control these norms of phi n of t. So actually I should need to control these norms in order to get boundedness of the sequences in the good spaces and apply my Aubin-Lyon's theorem, lemma, to get the convergence. So if you want to just draw a picture of that, the idea is that we're reasoning on a fixed time interval 0t. My time horizon Tn tends to infinity, but I'm fixed 0t. So whole 0 is my value here, but my final condition phi n is here. And for the energy estimates that I have, I can only get these energy estimates in terms of the condition at this time t here, phi n of t. So what I need to conclude is to show that this here is actually bounded. So phi n is bounded in L infinity of t, L2 of x. We actually show that it's even better than that. And in L infinity of t, H01 of x. And the idea to do that is to look into the Hamilton-Jacobi Bellman equation and in finite time horizon. And under the positivity of k and of the final condition, we can prove using comparison principle that phi, my function phi, is bounded between 0 and some constant c, and the L infinity H01 norm of phi is also bounded by some constant c, depending only on the final condition and geometrical properties and of omega and my function. how do we do this? Now, to prove the bounds on phi, we use the comparison principle. We can compare, for instance, with the solution of this equation here, the torsion equation, which can be seen as the expected time to leave the domain if we only have Brownian motion. And by doing the comparison principle between psi and phi plus the L infinity norm of psi, we can prove that phi is bounded by upper bounded by this quantity, which only depends on our domain and on the L infinity norm of psi and on u, and it's lower bound by 0. Of course, there are many technical details that you have to check in order to be able to apply this comparison principle. I'm skipping them here. And then to prove the L infinity H0 on norm, we can just take the derivative of the L2 norm, and then using that phi is bounded, I can get in the at first a bound on the integral of the H01 norm of phi, so L2 H01. And taking the derivative of the H01 norm, we can actually improve this L2 H01 bound into an L infinity H01 bound, because by using this equality here and doing some standard estimates using Young inequality and Granoff lemma, we can prove that the punctual value here of the H01 norm is bounded by some constant times the L2 H01 norm in some time interval of length 1. And so this proves me the bound L infinity H1. Of course, there are some problems here in the final time. You have to do a very somewhat different reasoning when you're close to the final time, but that's not that's quite easy. And so with this, what you can show, what you have just shown, is that these two quantities that we have here that were the problem, we can actually bound them only in terms of geometrical properties of omega and nu, and things that are bounded in L infinity and H01. So essentially, it's just as if this is just a constant depending on capital T. And then we have boundaries in the good spaces, and the Brownian's lemma allows me to conclude that we have compactness in the good space, and then convergence up to a subsequence. And then, as I said before, this allows us to show that that the limit is a solution to the meaningful game system, and so we have existence. So as I mentioned before, we did that at first for initial conditions for 0 in L2, but you can actually use parabolic regularization to improve that. And this parabolic regularization result is also important when considering the asymptotic behavior of solutions. So if I have a smooth solution of smooth subsolution of a very general here parabolic equation with smooth coefficients and bounded V and bounded G here, and my solution is non-negative, my subsolution is non-negative, then I can bound its L infinity norm at some time t plus delta by a constant times its LP norm in time delta plus the norms of the L infinity norms of the source terms here. And the constant here obviously depends on delta, it explodes as delta tends to 0. But essentially what you can get from here is that we get an improvement. If we are LP at some time, we instantaneously become L infinity for this kind of equations. So this is, there are other parabolic results like this stated in the literature, and they can be proved by some kind of Moser iteration arguments. And this is a pretty general formulation, which can be applied to Fokker-Planck and Hamilton-Jacobi Bellman equation if you take some terms here to be 0. But this is for smooth solutions. We can adapt this to non-smooth solutions of Fokker-Planck and Hamilton-Jacobi Bellman, but not in full generality, because we use some different regularization procedures for one or the other. And so I'm not going to get into details here. The idea is that for both equations, we can get estimates like this. And so this allows us to consider initial condition ρ0 in LP for any p greater than 1, because you know that instantaneously it becomes L infinity, and then we can apply everything for that we had before. And actually, with some extra work that is detailed in the paper, I'm not going to enter in details here, we can actually get existence of solutions to the Fokker-Planck equation and of solutions to the main field game system for initial conditions which are only in L1 with finite entropy. Now, last part of the talk, I think I still have some 5 minutes left. So I just want to discuss quickly the asymptotic behavior of our solution. So the meaningful game is a meaningful game where people want to leave a domain in minimal time. So, so the idea is that people want to go out. So the expected asymptotic behavior for whole is to tend to 0, and it would be really strange if it didn't. So thankfully for us, we can prove that it indeed converges to 0, and it converges to 0 exponentially fast in LP for every P. And now the idea to prove this result is that we can first do it for P equals 1. Yeah, just a short comment. So usually if you have a Fokker-Planck equation with directly boundary condition and some nice velocity fields, we can show also that it converges to 0. But the good thing here is that it converges exponentially fast and in every LP for every P from 1 to infinity. So we also have a uniform convergence to 0. And so we first prove that for P equals 1, in which case we know that the time derivative of the total mass is negative. And we have that a very important property in which we use the mean field game structure of the problem, that is the coupling between the equations on ρ and phi, which shows me that the time derivative of the product ρ phi is actually minus the total mass of ρ. And using this, we can actually estimate minus the total mass of ρ by the integral of ρ phi divided by dl infinity norm of phi. Just to recall, we have just shown that this thing is bounded, so the dl infinity norm is finite, and then we can use this to obtain the exponential decay of the quantity ρ phi with some rate lambda here that depends on 1 over dl infinity norm of phi. And using the fact that ρ is also non-increasing, we can also prove that ρ converges exponentially as well. Now, if you want, the second case is to improve this a little bit and get some P strictly greater than 1. We can do that for P equal to 2. And taking the time derivative of the altitude norm, we can show by some standard estimates and Gronall lemma that it increases exponentially. I mean, we have an exponential bound on its increase with some rate gamma here. And so we can interpolate. We can just take a space LP for P sufficient close to L1, such that the exponential convergence in L1 is more important than the exponential bound that we have in L2. And so this interpolation procedure gives us exponential conversion in LP for some P strictly greater than 1. And then we use the parabolic regularization to get that to any P, because thanks to the parabolic regularization, we can bound the L infinity norm by the LP norm. So if this one converges exponentially to 0, this one will also converge exponentially to 0, and just have a difference of time t and t plus delta here. But of course, it converges for t plus delta, it converges for the whole sequence. And so applying this, we can get the exponential convergence. Now, just a short word on the asymptotic behavior of phi. So the idea is that if everybody leaves the domain asymptotically, the idea is that asymptotically, the minimal time to leave the domain should be the minimal time to leave the domain when there's no one in the domain. So the idea is that we expect the solution phi to converge to a solution of this stationary problem here, kappa of 0 instead of kappa of ρ. So this solution, capital psi here with directly boundary condition, is the minimal time to reach the boundary when the density of agents is 0, and you can prove that this problem here admits a unique solution. And we can prove that any solution of the mean system, the value function converges to this as time tends to infinity, both in L infinity and so in any LP, and in age 0, 1. And the strategy of the proof is the following. The idea is that if we translate our phi by some sequence of time t and tending to infinity, we can prove that this converges in L2 H01 up to extraction of subsequences to some phi bar that solves this equation here. So this is essentially the equation of psi, but with also the time derivative here. So we know that psi is the solution of this, and we want to prove that the phi bar is also equal to psi. And we do that by comparison. So we consider two other solutions, which will approximate this phi bar from below and from above. So ut is the solution of the same equation with 0 final condition time capital T. Vt is the solution of the same equation, but with final condition phi plus m, where phi is the solution of this equation here, and m is large enough. And by a comparison principle, we have that phi bar is in between ut and vt. But these U capital T and V capital T here, they have some monotonicity properties with respect to the final time where we impose the zero condition here and the phi plus m condition here. And these monotonicity properties show that they are non-decreasing for U, non-increasing for V. And so they converge almost everywhere to as the time capital T tends to infinity. And we can prove that their limit necessarily must be the unique solution to our stationary problem. And so in this way, we prove that phi bar is equal to psi. And this gives us a convergence in L to H01, which we can improve to L infinity using the parabolic regularization result that I have shown you before in some slides before. And this also gives me, using the fact that phi is bounded in L2, H2, we can also work a little bit more to get the convergence in H1. So this implication here, I'm not going to tell it because my time is over and this is all I had prepared to say. So thank you for your attention.